So if you're taking Dr. Yampolsky's artificial intelligence class, you should be well acquainted with the traveling salesman problem by now. The basic problem definition of the traveling salesman problem is that given a list of cities and the distances between each pair of cities, what's the shortest possible route that visits each city exactly once and then returns to the original city? So this particular problem is a very famous problem in computer science, and it's one that belongs to the family of problems known as NP-complete, in which there's no answer that can be solved in, no answer exists for this problem that can be solved in polynomial time. So the problem here is that for any set of cities larger than about 10 or 12, the time and resource costs of checking all the feasible answers to the problem becomes literally impossible. It's so big that most computers can't handle it, or there's not enough time in the universe in order to compute an answer. So this means that, as the number of nodes in our problem increases linearly, the computational time increases exponentially. However, just because we can't run every single possible combination of answers doesn't mean that we can't solve the problem. And there are many heuristics to solving the traveling salesman problem that exist that can give us to a reasonably acceptable answer, if not optimal. And some of these heuristics include 2-op, 3-op, closest edge insertion, genetic algorithms, simulated annealing, A-star, and the one we're going to talk about today, which is branch and bound. So branch and bound was first proposed by Land and Dewig in 1960 for discrete programming. Branch and bound will always find the optimal solution, although in some very worst case scenarios, this could mean doing an exhaustive search, even though it is highly unlikely. In most cases, a large part of our search space can be pruned and save us substantial time in finding an answer. So branch and bound is very similar to the A-star algorithm, and it works in kind of the same fashion as depth-first search, and it is also closely related to backtracking. So branch and bound gets its name from the way that the search is performed. So as we traverse different branches of the problem, we will use the lower bound to find an optimal solution. So we're going to be recursively dividing the problem up into subproblems and then bounding the solution each step of the way. So in other words, we will repeatedly compute a feasible solution, then we'll add a constraint that restricts the set of feasible solutions to those that yield the shortest path, and then the end result will be an optimal solution, which includes all cities in our traveling salesman problem. So in this video, we're going to walk through an entire example of solving a traveling salesman problem using a trivial-sized data set consisting of 5 cities. And again, for those of you in Dr. Yampolsky's class, this is the same 5-city problem that was assigned for Project 1. So when we're done working through this example, we can check that solution against the solution we got in Project 1 to see if our answers match. So the only difference is that in Project 1, the distances weren't rounded off, so I rounded them off in this example just to make it a little more understandable. So this is the basic description of how the branch and bound algorithm works. We're going to start by selecting a starting city, and then we're going to reduce our cost matrix to establish a lower bound for our current node. We'll expand the current node, and then we'll compute lower bounds for all feasible routes at the current tree depth. And then we're going to repeat these 4 steps until our algorithm completes, and that is until every city in our tour has been visited. So for the traveling salesman problem, we can arbitrarily select a city since the starting city has no effect on our optimal solution. So we're going to just start at city 0. And before the demo gets started, this is just a quick little idea of what the state space for the traveling salesman problem looks like if you're starting at city 0. So for example, we can start at city 0, we can reach city 1, we can reach city 2, we can reach city 3, and we can reach city 4. So then if we decide that city 0 to city 3 is the best option, then our choices from 3 become 1, 2, and 4. So if 4 was our best option, then 1 and 2 are our next choices. And if 1 is our best option, then city 2 is the last one we visit before returning to city 0. So we begin our problem with a simple adjacency matrix which shows the distances between all sets of our cities. So from city 0 to city 1, you can see the cost is 12 miles, city 0 to city 2, 34, city 0 to city 3, 47, and so on. So now our first step in running the branch and bound algorithm is to reduce this adjacency matrix. And reducing the matrix means that each column and each row will have at least one value in the column or row that's equal to 0. And if there isn't one value or more in each column or row that equals 0, then we will reduce it by the minimum value in that row or column. So in our first row, we see that there are no values of 0. So we pick our minimum value, which is 12. And now we're going to subtract 12 from every single value in the first row. So 12 minus 12 is 0. And then we take 12 from 34, and that gives us 22. 12 from 47, 35. And 12 from 27 gives us 15. So then we move on to row 2, or I'll refer to it as row 1, so the indexing doesn't throw us. Again, our minimum value in row 1 is 12, so that becomes 0. 22 minus 12 becomes 10. 44 minus 12, 32. And 17 minus 12 is 5. Then we move on to row 2. No zeros, and our minimum value is 19. So we take 19 from 34, and we get 15. We take 19 from 22, that gives us 3. And then we take 19 from 45 for 26, and 19 from 19 is 0. Row 3, again, no 0, so we pick our minimum, and our minimum here is 44. So we take 44 from 47, and that leaves us with 3. We take 44 from 44 for our 0. 45 minus 44 is 1. And then 57 minus 44 is 13. Moving on to row 4, again, no 0, so we must reduce. Our minimum is 17. 27 minus 17 leaves us with 10. 17 minus 17 is 0. 19 minus 17 is 2. 57 minus 17 is 40. And then we are done with our rows. So now we move on to reducing our columns. And in column 0, we have a 0, so no further reduction is needed. Column 1, also 0, for no further reduction. Column 2, we can reduce, and our minimum here is 1. So we take 22 minus 1 for 21, 10 minus 1 for 9, 1 minus 1, 0, 2 minus 1, it's 1. Column 3 can also be reduced, and our minimum in column 3 is 26. So 35 minus 26 is 9. 32 minus 26, 6. 26 minus 26, 0. 40 minus 26 is 14. And then column 4 does not need to be further reduced. So to get our lower bound estimate coming from city 0, we add up all of these reduction values to the right and then along the bottom. So we take 12 plus 12 plus 19 plus 44 plus 17. And then for the columns, we take 1 plus 26. And that gives us our lower bound estimate as 131. So we'll go back over to our tree that we've started, and we will note that the lower bound is 131. And then we'll expand this node. And now we will investigate in order nodes 1, 2, 3, and 4. So we're starting now with our reduced matrix. And the first step for traveling from city 0 to city 1, we're going to make every value in row 0 infinity. And then every value in column 1 will also be infinity. And then we know we're not going to travel back from city 1 to city 0, so we can also make this value infinity as well. And then we begin our reduction. So we can't reduce the first row, or row 0, sorry. Row 1 can be reduced, and the minimum is 5, so we'll take 9 minus 5 for 4. 6 minus 5 is 1, and 5 minus 5, 0. Row 2 is already reduced. Row 3 is already reduced. And row 4 is not reduced, and our minimum value is 1. So we take 10 minus 1 and get 9. 1 minus 1 and get 0. And 14 minus 1 for 13. And then we reduce our columns. Column 0 has a minimum value of 3, so we're going to take 15 minus 3, and we get 12. 3 minus 3 is 0, and 9 minus 3 for 6. Column 1 is already reduced. Column 2 is reduced. Column 3 is reduced. And column 4 is already reduced. So then we add up all the values once again that we've reduced. So we have 5 plus 1 plus 3. And that gives us a total of 9. So to compute our new lower bound, we're going to take the cost of traveling from 0 to 1 plus the lower bound that exists at 0 plus any new reduction. So if we go back to our original reduced matrix, we see that the cost of traveling from 0 to 1 is 0. And then we add our lower bound, which is 131, and then our new reduction, which is 9, and that gives us a new lower bound estimate of 140. So we go to our tree and we add the lower bound estimate for 0 to 1 as 140. And then we move on and we check 0 to 2. First step, make everything in row 0 infinity, everything in column 2 infinity, and then we're not traveling back from 2 to 0, so that also becomes infinity. Row 0 already reduced, row 1 already reduced, row 2 already reduced, row 3 reduced, row 4 is reduced, and then likewise all of our columns are already reduced as well. So this gives us a new reduction of 0. So now we compute our new lower bound for traveling from 0 to 2, and we go to our originally reduced matrix, and we find that traveling from 0 to 2 costs 21 miles. And then we add our lower bound, which was 131, and then the new reduction, which is 0, and that gives us a lower bound for this city of 152. So we go back to our tree and we plug in 152. Now we're going from 0 to 3. Make everything in row 0 infinity, everything in column 3 infinity, and then we're not traveling back from 3 to 0, so that's also infinity. And then we begin our reduction. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So our total cost reduction for 0 to 3 is 0. So we compute our new lower bound. We look for the cost from city 0 to city 3, and that's 9. And then we add in our lower bound from city 0, and that's still 131, of course. And then we add our new reduction, which is 0, and that gives us 140. So we go back to our tree, and we note our new lower bound for 0 to 3 as 140. And now we explore 0 to 4. So you know the drill. We make row 0 infinity, and column 4 infinity. And then we're not traveling back from 4 to 0, so that also becomes infinity. And then we start reducing, so 0, 0, 0, 0, and 0. And then our columns, 0, 0, 0, 0, and 0. So our new reduction for 0 to 4 is 0. So we compute our lower bound. We look for the cost from city 0 to city 4, and that's 15. And then we add the lower bound from city 0, which we know by now is 131, sorry. And then the new reduction, which again was 0. And we add that up, and our lower bound for 0 to 4 is 146. So now we want to determine which node we want to explore and expand and explore next. So we look for our lowest lower bound, and we see that both city 1 and city 3 are tied at 140. So we could choose either one of these to explore, but we'll just go in order. And so we'll expand city 1. And then we'll see that we can explore city 2, city 3, and city 4. So starting with our reduced matrix from 0 to 1, we'll now travel from 1 to 2. So we make everything in row 1 infinity, and everything in column 2 infinity. And then we start reducing. So 0, 0, 0, 0. And then row 4 we can reduce. So the minimum value is 6. So we take 6 minus 6 for 0, and 13 minus 6 for 7. And now we reduce our columns. 0, 0, 0, 0, 0. And that gives us a total new reduction of 6. So again, we'll compute our lower bound, and we'll look for the cost from 1 to 2, and that's 4. And then we'll add our lower bound from city 1, and that's 140. And then we'll add any new reduction, which is 6. So our lower bound from 0 to 1 to 2 is 150. So now exploring 0, 1, 3, we will again make row 1 all infinity, column 3 infinity, and then we begin our reduction. So 0, 0, 0, 0, 0, and then our columns, 0, 0, 0, 0, 0. So our new reduction is 0. So now we look for the cost from 1 to 3, and we find that that is 1. And then we add in our lower bound, which is 140, and then our new reduction of 0, and that gives us a lower bound of 141. And now we're ready to explore city number 4. So we'll make, once again, city number 1 infinity, column 4 infinity, and then begin our reduction. So 0, 0, 0, 0, 0, and then it looks like all zeros across the bottom as well. And that gives us a new reduction value of 0. So now we look up the cost of traveling from 1 to 4, and the cost is 0. And then we add our lower bound, which is 140. And then we add our new reduction, which is 0. And that gives us a total of 140. So now we want to compare this new lower bound that we got on city 4 to all of the other values that are a level higher in the tree. And we see that we have nothing that's lower than 140, so we're going to continue on down the tree, and we're going to expand city 4 from city 1. And our two options are going to city 2 and city 3. So we will go to city 2 first, using our reduced adjacency matrix from our last step. So we're going to turn row 4 into infinity, column 2 to infinity. As you can see, we don't have many values left in our matrix. It's becoming quite sparse, so we'll run through this really quick. Basically everything here is going to be 0. Which of course makes our new reduction 0. So now we want to look at the cost of going from city 4 to city 2, and that's 0. And then we'll add our lower bound, which was 140, and then our new reduction, which is 0. And that gives us a total of 140. So we'll jot this down under city 2, and we will investigate city 3. So again, we're going to make row 4 infinity, column 3 infinity, and then we begin our reduction to 0, 0, and then row 2 can be reduced, so we take 12 minus 12, and that leaves us with 0, and then 0, 0. And then as you can see, for all of the columns, there's no remaining values higher than 0, so we'll fill all these in as 0. And that gives us a total new reduction for city 3 of 12. So we'll compute our lower bound, and we're looking for the cost from city 4 to city 3. And that cost is 13. And then we add in our lower bound of 140. And then our new reduction of 12. And it looks like we definitely don't want to go this way, as we get a total cost of 165 for our lower bound. So looking at our tree, from city 2, we're still less than or equal to any of the remaining lower bounds. So we're going to expand this to our one remaining city, which is city 3. And so we turn row 2 to infinity. And we skip to the end, and everything is reduced to 0 for a new reduction value of 0. So then we look at our cost from 2 to 3. 2 to 3 is 0. And then our lower bound is 140. And then our new reduction is 0, giving us a total of 140. And then if we compare our lower bound of 140 at the end of our tree here, we still see that that is the lowest bound on the tree, which means we have found the optimal solution. And then if we wanted to check this, as I was mentioning in Dr. Yampolsky's artificial intelligence class, this is the problem that we worked on in project 1 for the traveling salesman problem of size 5. We found out that we could solve this by brute force in about 3 microseconds, and the solution given to us in that problem was 0, 1, 4, 2, 3, which is exactly the same solution that we came up by using branch and bound.